So again, as I said a few minutes ago, this topic is from Chapter 9. Chapter 9 is about orbitals and the way they change. We've learned about orbitals already once this year. We talked about electrons. That was before any bonding happened. When we just look at non-bonding atoms and the electrons that are arranged around them, s orbitals are spherical. They just go around the nucleus. P orbitals are dumbbell-shaped. They've got an egg-shaped thing here and an egg-shaped thing here, and that's the nucleus in the middle. And there's 3 of them in any one sublevel. There's 3 p orbitals. And then the D's have that clover shape. The F's have that wild clover shape. Now, what happens is when atoms start to bond together, their orbitals change. They don't have the same looking and shaped orbitals anymore. That's what this topic called hybridization is referring to. Hybridization is the changing of an atom's orbitals so that it can bond appropriately. Now, we learned about carbon. We didn't learn anything about carbon bonding. That came later. But the first time we learned about carbon, we learned that carbon has 6 electrons. And there are 2 electrons in 1s, which is not shown here, it'll be down here. And then 2 electrons in 2s, and 2 electrons in 2p. 1s2, 2s2, 2p2. I'm leaving the 1s electrons out because I'm only focusing on the valence electrons. Because when we're talking about bonding, we only care about the valence electrons. We know also, though, that when carbon will bond to hydrogen, you got it, good. When carbon bonds to hydrogen, it has 4 bonds that it makes, and all 4 of those bonds are the exact same energy. Well, how can it be that an electron orbital arrangement like this would be able to give 4 bonds all the same energy? It looks like there's only 2 electrons that could bond, yet it's able to make 4. And what's it doing with that pair of electrons? It's already paired up. Well, when carbon's not bonding to anything, this is the way its electrons look. However, now carbon is bonding to something, so we think that carbon had to take those electrons and change them somehow, and rearrange them. And that process of rearranging, we try to explain by calling it hybridization. A hybrid is something that's kind of a blend or a mix of 2 different things. Like when you crossbreed dogs, it's a hybrid. Yeah. A cockapoo, like, is a hybrid. Cocker spaniel poodle. Right? I tell you. Hybridization is in chapter 9. No, I'm going to try to get to some of chapter 10 today. In the molecular attractions are chapter 10. Yeah, labradoodle is another example. Yeah, that's a hybrid. It's a mix of 2 things. So, hybridization of atomic orbitals is not as much fun as talking about dogs. But yeah, carbon not bonding to anything has its electrons arranged like this. What you learned before was not false, it's not wrong, it's true, until carbon tries to bond with something, then it rearranges its orbital. When carbon needs to make 4 different bonds, it takes those 4 valence orbitals and it makes them all the same energy. And it redistributes the electrons too, 1 electron in each. Now, when this is done, it's called Sp3 hybridization. What did that mean? That term means that there's 1 s. So it could say s with a superscript 1, but they just leave the 1 off. And 3 p's, so that's where that 3 comes from. It means there's 1 s and 3 p's, 4 orbitals that all make themselves the same energy. And so all 4 of those bonds are the exact same energy. It's not one's weaker than another. They're all the same. Yes?
Why is it 3? Because there's 2 s electrons.
No, it's not counting electrons, it's counting how many orbitals. 1 orbital from s and 3 from p.
Oh.
Yeah, it's how many orbitals. Okay. Yes?
But they're not all 3 orbitals are being taken, are they? From the p?
To make CH4, yeah, you need 4 orbitals on that carbon to make 4 different bonds, all the exact same energy.
So what it's doing is actually just taking one of the s's, putting it into the 3rd p, and kind of...
Yes, it's taking these 4 orbitals. Remember, that s electron, or that s orbital was round, spherical in shape. The p's are all dumbbell shaped. it's taking those 4 orbitals, which all have, well, the 3 p's have the same shape, but which all have different orientations, and it makes 4 new orbitals for itself. And the way those orbitals look, now I'm not going to draw this very well, because remember, notice the coordination number on the carbon. It's a 4, coordination number of 4. You're going to find, and I'll just say it right now, that it's the coordination number that dictates what the hybridization turns out to be. If this coordination number is 4, that means carbon needs 4 orbitals to hybridize. And that's why it's an S and 3 p's. So those 4 orbitals are going to look like this. Here's the carbon in the middle. And then rather than having a spherical and then 3 that are dumbbell shaped, it takes and makes. That's where we get the tetrahedral shape, where the angle there is 109.5. Those are the hybridized orbitals that dictate the shapes that we learned. So now this is like our tripod look. You got one kind of coming out and one kind of coming out and one going back behind the board. So I'm trying to draw it to look like 3-dimensional on a 2-dimensional board. But yeah, that's where we get our tetrahedral shape from. Now these orbitals don't look like they used to. I don't have a round orbital in there anymore. They rearranged, they hybridized. Yes?
On the M-STEP test, they asked the question, why does carbon like attract others or something? So like, this is a choice for 4 electrons.
Nice. So you all knew that, I hope.
Yeah.
No, I purposely chose the wrong answer because.
Just to spite your school, shut up?
Yes.
Darn it. Anything else about this? You're the first one that said that about the end stuff. Yeah? Everybody else is just filling in blind opals, I guess.
Yeah.
You're actually taking
Well,
it.
It doesn't count, so what's the
All right, Mohammed.
puzzle?
Now, you know how when we did the shapes, we learned that when it has 4 atoms and lone pairs on it, that's got a coordination number of 4. And those orbitals spread out as far as they can get from each other. Hybridization is just describing, it's the exact same thing. It's the hybridized orbital. When we talked about electrons a few weeks ago, I told you that S electron, okay, here's the nucleus. The S electrons were spherical in shape. There's an S orbital, and there's 2s. So this would be 1s, and there's 2s. And then 2p makes these dumbbell-shaped things. And then this 2p. And then the third one is out of the board and into the board. Oh, they're all perpendicular to each other. Do you remember learning about that? Okay. Now, the 1s electrons, they're not the valence electrons. They're already filled. They're not going to do anything. So we just ignore those completely. They're there, but they don't do anything. So I'm just going to erase them
Do you just count the outermost?
because I don't care about them. You only count the outermost ones, yes. So we're caring about. So now I didn't draw the third p orbital. And again, because this is a 2-dimensional thing, it would be coming out and going back behind the board. That represents 4 different orbitals. When carbon has to make 4 bonds, when it's got a coordination number of 4, it can't leave its orbitals like that. It can't bond to 4 things with orbital electrons in that kind of arrangement. So it's going to take and rearrange its orbitals to look like this. This is 4 orbitals. It's the same as those 4 orbitals, but they've been reshaped and rearranged so that you have 4 all coming off the carbon and all the same shape. So the 4 hydrogens that come along are going to bond and overlap their electrons with the carbon's electrons. And now they're going to all be as far apart around on the carbon as possible. So the hybridization is just a description of how many electrons or how many orbitals have rearranged.
Well, like for the first one over there,
Yeah.
like in the thing you drew it, there's only like 2s and 2p over there, but then how do you get like?
Well, 2p has 3 different orbitals in it. Here's 1 orbital, here's 2 orbitals, and then the third one is perpendicular to those. So when we talk about coordination number is the same as how many orbitals had to hybridize. This thing having a coordination number of 4 means all 4 of carbon's valence orbitals had to be the same energy. When I say hybridize, they need to be the same energy. And like equal distant from each other, which makes them 109.5 degrees from each other. Now, if you're still fuzzy, just hang out for a moment. We've seen just a coordination number of 4. Let's take a one with the look at when the coordination number is only 3. Still carbon in the middle. Now, the example I'm going to use here is this H2CO molecule. In H2Cl, what's the coordination number around the carbon?
3.
A 3. Mohammed, I want you to see this. Do you have it on your paper there?
What? No, I'm gonna write it.
Okay, but don't write it down yet. I just want you to see this. This carbon right here, this molecule has a carbon as the central atom. It has a coordination number of 3. 1, 2, 3. Do you remember how 3 things will arrange themselves around the carbon with the coordination number 3? They go trigonal planar. They go 120 degrees from each other. That means that the carbon only needs to take 3 orbitals and hybridize them. So when it's not bonding, the orbitals look like this. When it is bonding and has a coordination number 3, it only needs 3 of these 4 orbitals to make the same energy. So it's going to take the S and 2 of its P's. And that's what I have here. This is the S and 2 of the P's. They all now have the same energy. One of the P's didn't need the same energy, and so it just stays there as a non-hybridized P. Yes?
So does that outsider make the pi bond?
That's the one that makes the pi bond. That's
Is that
right.
why it's called a pi bond?
That's exactly why it's called a pi bond, because the Greek letter pi means P.
Oh.
Yep. And these make sigma bonds because they took the hybridized sp whatever, and that's where the names come from. So looking back at this, now this is something that you've learned before. Single bonds are always called sigma bonds. Single bonds are sigma bonds. When you have a double bond, the first one between them is a sigma bond. That's with the hybridized orbital. And then the second one is a pi bond. That's with the p orbital that didn't hybridize. So that's what it's saying up here. From the previous slide, the carbon in the middle had a coordination number of 4. That means it needed the S and all 3 P's to all have the same energy. In a case like this, we only need the S and 2 of the P's to have the same energy because the coordination number is only 3. So we call the hybridization of this one sp2. It took the S and only needed 2 P's to make the same energy. Now, the coordination number of 3 means that those 3 orbitals are going to spread as far as they can get from each other, and that's why we get the shape of the triangle, trigonal plane. So I'll pause a moment. If you want to go ahead and write that down, I'll be quiet for a minute for you to write and digest. Yes?
Is there like an SP4?
No. However, what about when our coordination number is 5?
Sp3D1. Yeah.
Yeah, when our coordination number is 5 or 6, I told you that not all elements can have a coordination number of 5. What elements can have a coordination number of 5?
Everything that has a d orbital.
Third row or bigger.
Yeah.
Remember I told you that before, third row or bigger, like sulfur and phosphorus on my periodic table rolled up, but sulfur, phosphorus, those are in the third row. They're filling the third energy level. Come on. Come on. Okay, I'll just hold it. So these elements, they're in the third row, they're filling the third energy level. If you have a coordination number of 5, that means that these have been able to take on more electrons than what their valence shell allows. So they're going to have orbitals to put those electrons in. They wind up taking some of their 3D electrons and hybridizing those with the S and the P's. So you can have sp3d or sp3d2, where it takes an S and the 3 P's and then 1 or 2 of the D orbitals, depending on what the coordination number is. Yes?
So energy levels go, say, 2p and then 3s and then 3d and then 3p.
No, the D is higher than P, so it goes 3S, 3P, and then 3D. That's the order they go in. Here's 3S, and then over to 3P, and then down to 3D.
And then 4s.
So it ignores the 4S, yeah, when it hybridizes.
So then 4s